Welcome everyone. Thank you for joining us for today's webinar. Jason Carroll will be presenting on expanding plant power capacity in a cost-effective manner. Just a little housekeeping before we get started. This webinar is being recorded and all attendees have been placed in listen-only mode. We will open the floor up for discussion during the Q&A portion of the presentation so we can have open discussion and questions. You can also type your questions into the chat box, and I can call the questions out if you don't want to have an open discussion. I'd first like to introduce our Vice President of Business Development, Mr. Kenny Darbone. He's going to talk a little bit about our company, and he will also introduce Jason. With that, I'll hand it over to you, Kenny.
Thank you, Allie. Good morning, everyone. My name, as Allie just mentioned, is Kenny Darbone, and I'm the Business Development Vice President here at CDI. On behalf of CDI Engineering Solutions, I want to again thank you all for joining us today for the webinar on expanding plant power capacity in a cost-effective manner. CDI is a full-service provider of engineering, procurement, and construction management services. And as you'll see listed on the next slide, we have offices across the Gulf Coast and the Mid-Atlantic area. From these offices, we service customers across the United States. Since COVID-19, CDI has began offering webinars in order to drill down into some of the services listed on the previous slide. We typically choose these topics based on surveys that we send out to our customers and ask for their hot topics or areas of interest. So if there are any other topics of interest that you might want us to present in the future, please let us know. There'll be contact information at the last slide that you can reach out to us on. Today's presenter is Jason Carroll. Jason is the Electrical Department Manager out of our Houston, Texas office and is professionally licensed in Texas, Missouri, Indiana, Louisiana, and is an NCEES record holder. We need to ask Jason what that record is. He graduated with a BS from Missouri University and since has worked on many different projects and project sites, including refining, chemical, power generation, and commercial facilities. He has worked with voltage levels in the range of 120 volts to 35 kilovolts, as well as modeling distribution of power throughout the various sites in ETAP or SKM software suites. Jason, over to you.
Thanks, Kenny. So our agenda today is a brief discussion of some of the components of electrical distribution, ways of expanding electrical distribution in a cost-effective and creative manner, and a few alternate ways of powering gear in your plant and how that may impact reliability. But first, I want to take a safety moment. So safety first. You may have seen these stickers or signage similar to this. This is a basic arc flash label. The 2018 NFPA 70 requires that the owner of electrical equipment install field labels on equipment. These labels must display the nominal system voltage, the arc flash boundary, and at least one of the following two items, either the arc flash hazard PP category or the minimum arc rating of clothing and PPE. The rules surrounding this are mostly found in the NFPA 70E, such as requiring the labels to be reviewed every 5 years or less. OSHA has a few of their own points to consider as well. Also want to talk about common household electrical issues. It's possible that if you make an electrical circuit with your body, even at low currents, you can be what's called locked on or unable to let go from the electrical circuit. This is where GFCIs come in. For a child, it is above 3 to 5 milliamps. For an adult woman, typically above 68. And for an adult man, it's typically above 7 to 9 milliamps of current flowing through your body. Once it gets above these levels, you may be unable to actually let go. The longer you have power going through your body, the more damage you're going to sustain. And this is one reason why GFCI receptacles have become so helpful and even mandated by local jurisdictional code. It is recommended that GFCIs be tested monthly to ensure that they're in working condition. So power end users typically start with a power plant, here shown in red. This is normally some sort of a generating facility that outputs power at a medium voltage. This voltage is then stepped up to allow the power to be transmitted, as shown in blue, over very long distances without losing much power to resistance heat losses. Heat loss equation is basically current squared times the resistance in the wire. If you can reduce the current, then the heat losses will drop dramatically by a factor of being squared. So as per Ohm's law, V equals I times R. If the voltage increases and the current decreases. So this is why you see transmission lines transmitting at very high voltages. Once the voltage nears its end user location, it is stepped down, and this is shown in green. Depending on the location, this will normally be near a switchyard or inside one of the end user sites. Here's a basic online diagram. The squiggly lines represent transformers. These are normally at generation. Up at the top, these transformers are considered step-up transformers. Generating voltage may be around 18,000 volts and may be transmitted and stepped up at maybe perhaps 138,000 volts or higher. The circles in general represent the motors, or in this case at the top, the generators. The squares or rectangles, these are buses or breakers. This is where power can be directed to different paths or interrupted to prevent flow for various reasons. In general, looking at these diagrams, the higher the voltage is shown at the top normally, and the lower voltage is generally shown at the bottom. There are many different ways to set up your site distribution. Taking the methodic approach here are some basic things to consider in terms of capacity required, footprint of your electrical infrastructure, reliability, maintainability, and cost. Three of the most common bus breaker orientations are shown here. Here in red and pink, breaker and a half allows you to feed your loads from two separate sources. If you should lose one of these three breakers, all of your loads remain powered without interruption. This is more common for incoming higher voltages. All these breakers are normally remain closed. The simplest in orange is a single bus. This is the cheapest and easiest to run, but if there's ever an interruption, the entire bus is shut down. Shown in green is a main tie main scheme. Under normal circumstances, the tie is open. This means power can't flow, but the main breakers are closed. Note there are three transformers from utility load on the far left and only one transformer from utility to load on the far right. Depending on the transformers, this may introduce a phase shift, and there could be many other issues to consider. So these sources are normally kept in an open transition relay coordination scheme. For comparison, here are some relative cost comparisons between different types of schemes. With the single bus being the baseline, you can see the costs may quickly increase. Though the cost increases with increased complexity, consider the reliability and maintenance. For example, if your breakers have a mean time to replace of 4 hours, how much would it cost your site if you lost power for those loads for those 4+ hours? This is where you can start to see if more complexity can achieve the reliability that's worth the investment for your site. So let's discuss expansion. The first step is to quantify your needed ampacity. Looking at all of your anticipated new loads and also future loads, determine how much power is needed and at which voltage levels it will be needed. Next, consider how critical your processes are. Will your site remain safe and profitable with the typical outages, or if a fault may occur, how much will it cost you if the gear compared to the gear cost if you lose process time? With your needed power in mind, discuss and plan with the utility. If you have a small site, this will be of minimal impact. But if you have a large site or a large power increase, the utility will probably want to know and may even study it. This may take a while to work out with the utility, so you should continue to work in parallel with your regular site implementation. Knowing the ampacity and voltage levels, now consider where on site you can locate your new gear. You need to plan for how you expect the utility power to get onto your site. You want to keep your substation or switchyard out of any hazardous area, and ideally you'd like to locate it close to where you are planning for the new loads to be, so you won't incur additional costs for perhaps longer cable runs or infrastructure to hold the cables. And you also want to limit access to the switchyard area to only authorized personnel. This can normally be done easily with a fence, but you wouldn't want to block a typical well-traveled pathway. At this stage, you need to prove out what you think you need and what you have planned as available or to be added and subtracted from your electrical sources and electrical loads. This will allow you to develop things such as your short circuit rating for your equipment, power factor for coordination with utility. If you have large or high voltage loads, you may want to consider harmonics in the system as well for power factor correction capacitor banks. Voltage drop your cables and busing with loads far and away, and motor starting. And this can also be the beginnings of your arc flashing reliability study. There are several new technologies that have been developed in the past 30 years that have added safety and reliability to electrical systems. Some basic examples of this are the relays. They've migrated from mechanical to electronic to 100% electronic relays that even now have light sensors which can detect arc flash events. The oil in the transformers is also safer for both people and the environment, getting rid of all PCBs. And another big one, arc flash resistant gear. These can divert arc flash gases away from personnel. Different schemes of breakers and equipment have also been shown to enhance reliability. And we're going to talk about some of those here soon. A quantifiable, objective way to determine system reliability is to conduct a PRA, or a probabilistic risk assessment. IEEE 493 has outlined a number of points in performing this assessment, and various software companies have actually made this much more practical to perform. In addition, if you already have SKM or ETAP model available, this can be a very quick and easy way to develop additional source for your company and looking at the reliability. Here's a simple example of using a few breakers and transformers. We have a single bus design down to the 40 volt, which then uses a main time main scheme. There is an optional generator turned off. Looking at this, we can see a baseline for the worst expected hours per year for this example if it's offline. The tie breakers are open and power is available to both mains. If we turn the generator on, the reliability of panel 8 becomes about twice as good as it was before. Here we have the worst case. Panel 1 is about 25.21 hours per year offline when the generator is off and the tie breakers are both closed. So the reliability here got worse by only about 1 hour per year. Now if we turn the generator on and add to the utility source, we see panel 7 8 went from about 24 hours per year offline to 13. This is a simple example of quantifying how an additional source will affect your reliability. Here's a more complicated example using a breaker and a half scheme for the main utility sources. This is feeding main tie mains at the 40 volt level. We have the generator off. Panel 16 is at 21 hours per year offline, and panel 18 is at 14 hours per year offline. Now simulating if one of the breakers and the breaker and a half scheme open due to fault or maintenance or even tripping, all the loads are still powered. We do, however, see the reliability for everything has now dropped. This alignment is like a single bus design. Panel 16 goes from 21 to 30 hours per year offline, and panel 18 goes from 14 to possibly 22 hours per year offline. Close all the breakers of the breaker and a half scheme, but now open one of the 40 volt main breakers and close the tie. Panel 16 is still sitting at about 22 instead of 21. Panel 18 goes from 14 to 16 hours per year offline. Here the generator is turned on. The results in panels 14 and 18 appear to have much better reliability. Panel 18 goes from 16 to 13. Through methodically noting the expected outages and costs associated with these outages, the likelihood of them occurring and affecting equipment downstream, you can reasonably determine if it's worth it to your site to add to additional reliability measures. Here's some examples of the estimated costs per year of services interrupted by any of these devices. This can help you pinpoint which devices have the biggest bang for your buck if you're to do a targeted system reliability improvement. For example, if you were to expand your site here at the 35 kV level, giving T2 some sort of redundancy or sub 2A an additional source input, you would have a large effect on your expected interrupting costs per year. I've circled those in red. I've chosen a few additional costs to look at, but T2 stands out as far and away the biggest one. So here we have a simple problem. Say you have a 12 kV lineup with only one spare breaker. This lamp is being fed by a transformer with a lot of spare capacity. You need to feed several more loads, but you only have one spare breaker. What do you do? What's the looking for a cheap and creative solution to maintain your loads. So one thing you can do is look at your transformer. Your transformer is only being utilized at about 1.5 MVA right now, but it's a 10 MVA transformer. The sub A is well loaded, but it has one spare breaker you can use. So if you were to use that one spare breaker to connect to your next sub, you might see the transformer can power that without having to buy another one. So again, this transformer is only using 15% of your capacity. Let's see if we can utilize that more to be more efficient with the gear we already have on site. So here I have a low flow diagram showing that transformer being connected with some new loads to this new sub B. Using that spare breaker, we power sub B, and that sub B would have additional spare breakers in it, and also powering the new loads that we have. Transformer still is only loaded at about 2 MVA, so still well underloaded. This will allow for possible future expansion. Okay, and with that, if everyone like, you can use a chat bot or chime in. If you have any questions, I'm happy to discuss.
Yeah, I'm unmuting all the lines so y'all can ask questions.
Sometimes we're asked to discuss how much time is required to conduct a reliability study. What we normally say is if we have a complete ETAP or SCAN model already available, then a reliability study or even an arc flash update to your site would actually take a lot less time than you might expect. The most intensive parts of these studies is surveying the site and creating an accurate model for your electrical system.
Okay, do we have any other questions, or is there anything else you wanted to cover up, Jason, before we wrap up?
That's about it. Another thing to consider if you are increasing your site capacity is your short circuit available current. When you're adding multiple sources, this can affect your short circuit availability for your gear, so that's something you'd want to consider as well. There's a number of things to consider, so a detailed analysis is required for these cases, but as you can see, saving tens of thousands or more dollars for your site is very possible. That's about all I have. If anyone has additional questions, I'd be happy to discuss.
Okay, well, thank you everyone so much for joining us. We really appreciate you being here. We are going to upload this webinar on YouTube, so you can check it or maybe send it to your coworkers. And we're also going to forward the slide deck along with contact information of Jason, Kenny, and Robert Billio in case you need to reach out to any of us. We'll go ahead and email that to the ones who have joined us. So we greatly appreciate again you being here. Thank you so much, and we look forward to the next webinar next month. Bye, everyone.
Thanks, everyone.